Welcome back. Today we're going to talk about iterative systems. And here the idea is the following. We have a linear transformation from Rn to itself. And we're going to take vector v in Rn and apply t to it, and then repeatedly apply it, iterate it. Apply t to v, and then t squared v, t cubed v, and so on. So that is to say, we have a matrix T, which is it's an n by n matrix. And what we're interested in is sort of seeing what happens, which is to say, you start with some arbitrary vector u and call it u naught, and that's going to be given. And what we'd like to do is find t u naught, and then find t u1, which is to say t squared u naught, and so on. Understand what the sequence of vectors is when you repeatedly apply t to the original vector. And that is to say, you're essentially computing the powers of this linear transformation and applying it to this given vector. So let's do a very simple example. Let's take n is equal to 1. Sort of obvious what happens when n is equal to 1. So this vector is just a number. Let's say it's 1. And then t is just a 1 by 1 matrix, which is, say, lambda. And, well, when you apply lambda, you just multiply by lambda, and then t squared, you get lambda squared, and t to the n is lambda to the n. So you're just computing powers of lambda. And if lambda is bigger than 1, this is going out to infinity. And if lambda is less than 1 in absolute value, it's going to 0. And as I said, the main point here is to compute the nth power of t, which in this case is very easy for a 1 by 1 matrix. It's just this number, lambda to the n. Okay, let's look at a simple 2 by 2 example. Let's say T is this silly diagonal matrix 2 1/3. So let's see, if V was 1 0, then T, this is an eigenvector with eigenvalue 2. So T to the k applied to this is going to be 2 to the k 0. And on the other hand, if v was 0, 1, then it's multiplying it by a third. So you're going to get 3 to the minus k. And let's draw the picture. If you start at 1, 0, it's going to move to the right and go out to infinity. So I'll just draw an arrow indicating you're going to the right. And on the other hand, if you started at 0, 1, the numbers are getting much smaller, so you're going towards 0. And on the other hand, if you started with some other point like 1, 1, well, you get a combination of these two behaviors. And let's see what happens. You start at 1, 1, and then the x-coordinate is going to go to infinity, but the y-coordinate is going to go to 0, so there'll be a bunch of points like this. And in the other direction, if you took negative powers of t, you'd be going this way. These should be familiar looking curves from the differential equations section. Here's another kind of example. Suppose I took this 2 by 2 matrix with radical 2's in it, radical 2 over 2's. And let's draw a picture. It involves the circle. And let's start at the point 1, 0. Well, let's see. If I apply this matrix to 1, 0, let's see, what do I get? I get radical 2 over 2 minus radical 2 over 2. So that's, let's see, that's this point right here. So this thing is rotation clockwise by pi over 4. So if we keep repeating it, we'll just keep going around the circle, an eighth of a circle each time. So here's t squared, t cubed, t to the 4th, t to the 5th, t to the 6th, t to the 7th, and t to the 8th. It takes you back where you started. So this thing is just moving points around the circle And when you do it 8 times, you get back where you started. All right, well, as I said, basically what this comes down to is how do you compute the powers of a matrix? So if I give you some n by n matrix, excuse me, and I want to compute its powers a to the k for all the different k's, how do I do that? Well, let's just look at a basic example. Let's take a matrix, I don't know, say about this matrix. Let's just try and compute its powers by hand. Well, let's see, when you multiply it by itself once, you get this thing. And let's see, what do you get? Minus 1, 10, minus 5, 14. That's not so clear. And now if you cube it, well, you have to multiply it by, multiply this by this, and you just do that, and, well, it is what it is. It's just some numbers, and there's no pattern at all. It's more or less impossible to figure out what it's going to be. This is no good. Computing powers of matrices like this is a thankless task. Now, before I did an example where B was diagonal, so for example, if B was this diagonal matrix, well, then it's really easy. It's just you're taking the kth powers on the diagonal. And that should sort of give us the hint about what we should do. If the matrix is diagonalizable, then you should diagonalize it. So if you're given a matrix A and you can diagonalize it, well, notice that if you, then it's very easy to compute the powers. So for example, if you take SA, S inverse times itself, that's D squared. But if you look on this side, that says that S of A squared, S inverse, is equal to D squared. So the S which diagonalizes A also diagonalizes all powers of A. So for example, if you want to diagonalize A cubed, you get D cubed. And so the conclusion from this is that to compute A to the K, you just write it as S inverse D to the K S. If you have the S which diagonalized A, then you can use this formula for computing powers. I should write in an intermediate step here. This formula comes from the following. S A to the K, S inverse is D to the K, and then you just bring the S's to the other side, and that's how you compute A to the K. So the moral of the story is what you really want to do is diagonalize your matrix, and then computing powers is easy. Okay, so let's go back to our example. Let's take this matrix 1, 2, minus 1, 4. This is the one I had before. Well, you compute its eigenvalues, and let's see, it turns out that the eigenvalues are 3 and 2. And the 2 eigenvector is found by finding the kernel of this matrix, which is to say you can use the vector 2, 1. And the 3 eigenvalue is found by the kernel of this matrix. You can use the vector 1, 1. And so this is something we've done a million times. The way you diagonalize this matrix is you write down, you get this identity. If you multiply on the right by the eigenvectors as columns and the left on the inverse, then it diagonalizes to give you 2, 3. Okay, so now we can use this to compute powers of this matrix. So, for example, let's see, so let me label these. I'm calling these SA, S inverse is equal to D. And so I write this as A is equal to S inverse DS, which is to say S inverse DS, like this. And now you can compute powers this way. So for example, that says that a to the k is S inverse 2 to the k, 3 to the k, s, which is quite easy. So let's just check, for example, when k is equal to 2, let's make sure we get the right answer. When k is equal to 2, let's just work it out. I get, this is a 4 and a 9 down the diagonal. And when I compute this, let's see, I get 8949 times this guy on the right. And when you work that out, that gives what I had before. And similarly for k is equal to 3, you do this calculation, 827, and you just do this calculation, and you can see that for any power of k, it's equally easy. You could do this for k is equal to 10, and without having to do it one step at a time, working your way up all the way from k is equal to 1. And here's the answer, and I think there was a misprint in one of the entries in the previous slide. This is the correct answer. Okay, so here's the general situation, the conclusion from this discussion. I have this n by n matrix A, and suppose I have an eigenvalue lambda with a corresponding eigenvector v. Well, it's obvious that AV is equal to lambda v, implies that a to the nv is lambda to the nv for any n. That's clear. So that basically tells you how to compute powers of a matrix as long as you have eigenvectors. So I'm going to concentrate on the case when the matrix has a basis of eigenvectors. So there's lambda i's and vi's form a basis. Then the way you compute a to the n in this basis is just you get powers, the appropriate powers in front of each vector. Let's say a to the k, I should say. You get lambda 1 to the k v1 and so on up to lambda n to the k vn. So as long as you choose this basis, it's quite easy to compute the powers of A. And this is just saying that if A was essentially saying that if A is diagonal, it's easy to compute. And this is totally equivalent to this calculation, which says that if you diagonalize something, then since computing the powers of the diagonal are just the powers of the lambdas, and when you diagonalize, that's what you get. That's essentially what we've done here in this formula in red. Okay, so let's go back now to our iterative system. Suppose I start with a vector u0, and I want to compute u1, which is t applied to u0, and then up to u k plus 1 is t applied to uk. Well, that's t squared applied to uk minus 1 and so on, although it's really just t to the k plus 1 applied to u0. And I'd like to figure out what these vectors are and graph them and understand their behavior. So here's the theorem. Suppose I'm given this linear transformation t from Rn to Rn, and I'm going to assume that it has a basis of eigenvectors, v1 through vn, with corresponding eigenvalues lambda 1 through lambda n. Well, then take this vector u0 and write it in the basis of eigenvectors. It's some c1 v1 up to ... cn vn. You can do that because this is a basis. And once you've done that, then you have a formula, a very simple formula for the uk's, and it's just a repeat of what I said on the previous slide. You just put in the powers the lambda I to the k in front of each of the corresponding eigenvectors. So that's just really an obvious restatement of what I had on the previous slide. All right. So now I want to talk about stability of these systems. It's very similar to the discussion about stability of differential equations. Notice that the zero vector is just fixed by all of these t's. If you apply t repeatedly to the zero vector, you just get the zero vector. So if you plot these trajectories the way I was doing earlier, well, this is just a point. It's just sitting there, just like the zero solution of a differential equation just sits there. But if you take some other point and apply powers of t to it, maybe it'll go off to infinity, or maybe it'll go back towards zero, or maybe it'll do something else. That's the question. Very similar to the setting for in differential equations. And what we do is we say that this zero solution is asymptotically stable. Well, I think you know what I'm going to say here. It's asymptotically stable if when you take any other vector, u, then when you apply t to it repeatedly to get these u to the k's, they go back towards zero. So that is to say, any vector in the vector space, any vector u, if you take the limit as k goes to infinity of t to the k applied to that vector, you get the zero vector. So that's natural. That's the natural notion of asymptotically stable in the setting of iterative systems, and this is the vector u here. Okay. So the question is, how do you tell if a system is stable or asymptotically stable or not? So here's the theorem. Suppose T is an n by n matrix. And then the zero vector is asymptotically stable exactly when the following condition holds. If and only if the absolute value of lambda is less than 1 for all eigenvalues of t. So you compute all of the eigenvalues, real or complex, and they'd better all have absolute value less than 1. Now, I'm not assuming that t is diagonalizable here, and the statement is true in general, but the essential case is when it's diagonalizable. And if it is diagonalizable, after diagonalizing it, you can make it look like this. And then when you apply t to the k, you're going to get lambda 1 to the k and so on, lambda n to the k down the diagonal. And this had better be going to 0. Well, when I say going to 0, I don't care if these things are positive or negative or even complex. So what matters is that the absolute value of these lambdas, lambda to the k's, had better be going to 0. And that happens, well, you can pull out the power, and then that'll happen if and only if the numbers are less than 1. If, never mind complex numbers, if you have a number that's bigger than 1, when you take its powers, it goes to infinity. And if you have a number less than 1 and you take its powers, it goes to 0. So it's really very simple. So here's a definition about a linear transformation or a matrix. This is just a little bit of terminology. The spectral radius of T is defined to be, it's written rho of T, and it's the maximum of the absolute values of the matrix. It's the max, it's a real number greater than or equal to 0, and it's the maximum of the absolute values of the eigenvalues. So with that definition, what we conclude is that the zero solution is asymptotically stable if and only if the spectral radius of T is less than 1. That is to say, the biggest eigenvalue and absolute value is less than 1. Fine. That's almost all I have to say. I just want to mention a little terminology. We say that a matrix or linear transformation is convergent if this holds, which is to say, we say it's convergent if when you take powers of it, that it and you apply it to any vector, it's always going to 0. So that's just another way of saying the same thing. So that is to say, with this terminology, a linear transformation is convergent if and only if its spectral radius is less than 1. And in the next lecture, I'll talk about the spectral radius some more and how one computes it.